Very good morning. We had started learning automata languages and computation subject, and unit 1 we had started with the central concepts of automata theory, where we covered this PDF mentioning language, alphabets, strings, words, their validity, various operations, and we mentioned that there are four ways of defining the language. One of them is finite automata. So we had mentioned sigma as a symbol which indicates alphabet, and usual convention is UVWX is used for strings, ABCs are used for symbols, epsilon or lambda are used for empty string or null string. This indicates length of the string. So this to the power, so exponential of the alphabet relationship is given here. This we had all covered. Then we had also mentioned sigma star closure or star operation as clean star closure. So wherein clean star closure is indicated by sigma star. Clean star closure comprises of all possible configurations of letters, including null closure. So you also have sigma plus, which is called as a plus operation, and it is except null, rest of all the possible combinations are there. So the relationship between positive closure and clean star closure is positive closure is equal to clean star closure minus null. So now we'll continue our discussion. We'll be going for automata, and let us not forget the name of our subject, automata, languages and computation. Here we deciphered the meaning of automata is automata is a plural of automaton. Automaton is anything which happens automatically, which actually represents a machine. It's a theoretical machine. So, and computation is all the mathematics or the task involved by a computer. And what is the importance of language? Language is used to communicate with the machine. Language is used to communicate with machine. So any computation involves CPU and memory. It also involves various kinds of memories like temporary memory, program memory, input memory, output memory. Say for example, you have this calculation, f of x is equal to x cube, and the value of x is given as 2, and the computation happens in the temporary memory, and the output memory will get the output. So this is what is an automaton. It's a machine. It's an abstract representation of a machine, which comprises of various kinds of memories. Now when I say automata, there are different kinds of automata distinguished by temporary memory. You have finite automata with no temporary memory. You have push-down automata having stack. You have Turing machines having random access memory. Now finite automata does not have temporary memory, having small computing power. Push-down automata has a stack. Turing machine has random access memory. If you look at the power of an automata, the hierarchy is lower power to more power. Lowest power is finite automata, followed by push-down automata, followed by Turing machine. We have taken already this importance of the word languages, and Any language will be either accepted or rejected by a finite automata. So a language comprises of a string. That string will be given as an output. The input. The finite automata will be taking that input, and in the output we'll be getting the accept state or a reject state. Let us say this is a transition graph representing a finite automata. Now what this graph comprises of? This graph comprises of nodes and edges. Typically any graph will be comprised of nodes and edges. Now these nodes will be called as states. So how many states are there? Q0, Q1, Q2, Q3, Q4, Q5. So total 6 states are there. Okay. So among them, this state Q4 with a double circle is a special state called as an accepting state. Now there is a state change from Q0 to Q1 upon input A, from Q1 to Q5 upon input A, from Q1 to Q2 upon input B, like that. So transition of state is occurring, state changes is occurring, right? Say for example, this is the input string given to the machine, A, B, B, A. So this input string consists of symbols A, B, C, D, right? And what is this A, B, C, D? They are part of the alphabet. They are part of the alphabet. This string is being given to this machine. And this machine, let us say, will start with A. And we are at the initial stage. Initial state is given by this arrow mark, right? And the accepting or the final state is given by this double circles. So at the initial stage, input is A will go to Q1, then input is B will go to Q2, then input is again B will go to Q3, input again is A will go to Q4. So as the input string is completed, we reach an accepting stage. So this indicates this language is accepted by the machine, right? So input is finished, so language is accepted. Similarly, take this case, A will go to Q1, B will go to Q2, again A will go to Q5, but Q5 is not an accepting state, so this language is rejected. Okay, similarly lambda, acceptance of lambda is rejected. Now let us say we have A, B. So first A, then second A, then B, we have reached an acceptance stage. This language is accepted. Similarly, we are at Q0. Once we give the input B, it will reach Q1, then again A Q2, then again B Q2, rejected. So let us take this example, A B B A. So at the initial stage Q0, A is input, then reaches Q1, B is input, then reaches Q2, B is input, then reaches Q3, A is input, then reaches Q4. That is an example of accept. So similarly here, this language has various alphabets represented by AB, AB, BA. So coming to the definition of finite automata. So the formal definition of finite automata, FA, is indicated by M. And M is a 5-tuple entity. How many tuples are there? 1, 2, 3, 4, 5 tuple entity. What are those tuples? Q, sigma, delta, Q0, F. So Q0 indicates the set of states. Sigma indicates input alphabet. Delta indicates transition function. Q0 indicates initial state. F indicates set of accepting states. F indicates set of accepting states. So let us say this is my finite state machine. What are the 5 tuples? Q is set of states. How many set of states are there? 6 set of states are there. Q0 is initial state. Q4 is acceptance state. Is it not? So you also have delta, which is a transition function, right? So say Q0 comma A will be Q1. Q1 comma B will be Q2. That indicates the transition function. Similarly, you have input alphabet. What are the input alphabet? A comma B, like this. So sigma is A comma B. Q is set of states Q0 to Q5. Q0 is initial state. F is final state, and delta is a transition function. So applied where? On set of states and alphabet, reaching to a new state. Okay. So let us say delta is a transition function. We are at Q0, input A is given, the next state is Q1. Similarly, we are at Q0, input is B, we reach Q5. We are at Q2, input is B, will reach Q3, like that. So this is the transition graph, and this is the transition table. Same thing is there. The delta function is applied. We are at Q0, input A is given, we'll be reaching Q1. We are at Q0, input B is given, we'll be reaching Q5. Like that, this transition function table will be created. So you also have extended transition function given by delta star, where we have sigma star, various possibilities. Extended string will be there. So same, we are at a particular state, the string is given, we'll be reaching a particular state. Say for example, we have delta star Q0 comma AB. So Q0 given A will reach Q1. Q1 given B will reach Q2, like this. This is the extended transition function. Same thing here, delta star Q0 comma ABBA. So ABBA, it will be reaching the final or accepting states. So ABBBAA will be reaching Q5 state. So like that. So if you look at delta star Q0 AB, it will be reaching Q2. It will be delta of delta star of Q0 comma A. This is a simplification of that, right? I'll be skipping few for future discussion. So let us recollect our previous discussions. We have strings, okay, and the sigma is an alphabet having symbols ABC, and UVW here are the strings, and we have ABC symbols in the alphabet sigma. Then we can perform concatenation operations like here W and V. So let us say W is ABBA, V is BBBAA. We'll be concatenating them. We'll be performing the reverse operation of this. This is the length of ABBA is 4, length of A is 2, length of A is 1, like that. So length of concatenation also, let us say string U length is 3, string V length is 5. So the length of concatenation is 8. A string with no letters is indicated by lambda, and the length of lambda is 0. And lambda and string, the combination is same as string and lambda multiplication. Will be reaching the output will be the string only. So lambda ABBA lambda is equal to ABBA only. So these are the strings and these are the substrings, like AB is a substring of ABB. And let us say this is my ABB string. The prefix is lambda. For this the prefix is A. For this the prefix is AB, like that. So you have prefixes and suffixes. The star operation, we know that this is called as a clean star closure. And what is clean star closure? Set of all possible strings from alphabet sigma. So sigma is equal to A comma B. Sigma star indicates all possible strings including the null. So that is clean star closure. So this is called as a positive operation. What is the relationship between clean star operation and positive operation? Positive operation is equal to star operation minus lambda. What is a language? It's a subset of clean star closure. I'll be presently stopping here, and we'll be continuing our discussion in the next session. Thank you.